Before we begin going through normal and abnormal TCP/IP communications in this module, I want to go over some of the references and resources that are available for a network analyst. The first location, because we're working with Wireshark, would be the Wireshark webpage. Let me take you out there and I'll show you some of the areas and elements and information that's contained at www.wireshark.org. Now, of course, this page may change over time, but this is the main entrance to information about Wireshark. On the left-hand side, you will see there's an area to obtain help. The documentation for Wireshark is online, and it also comes with Wireshark. You'll see that there's the users directory available in a web page format or in a PDF format or in a Windows help file format. The man pages are also available online. And this is where you'll also find a list of the display filters. I'll open up that section just so you can see what's contained in the display filter reference area. For example, if I'm doing display filters dealing with TCP communications, I'll select the letter T, and there is the TCP protocol listed. I'll select that. And this area will show me all of the different field names and the syntax that I can use when setting those display filters. We'll go back to the documentation area. You'll see the release notes and the security advisories for Wireshark available online. And then the developer's guide is also available online in this section. Wireshark has several mailing lists. For users, you will see that announcements about the release, etc., will be in the Wireshark Announce list. There's also the community-driven Wireshark users mailing list. This is when people have problems or questions about Wireshark. They can post those questions to other users. Then there is also the developers mailing list. This is where any of the developers talking about what they're working on with Wireshark, they go through back and forth about things they would like to add, things that are working, things that aren't working. The Wireshark commits area is where you can get notifications as pieces of the code are checked in to Wireshark. And then you'll see there's a section there for masochists, which is the Wireshark bugs mailing list. And again, each of these are noted as to whether they're high volume or low volume. If you don't subscribe to one of these mailing lists, it doesn't matter. You can go to the archives and you could read what's been posted. In addition, there's a wiki page that focuses on Wireshark. The website is wiki.wireshark.org. Now in this page, in the wiki page for Wireshark, you'll find how-to information and how to edit the Wireshark wiki page. There's a wish list of things that people would like to have implemented in Wireshark. There's a bug list as well, and there's where you'll find some sample capture files. In addition, there's information on how to track down certain network problems using Wireshark. There's also information on preparing and installing Wireshark and T-Shark, using Wireshark and T-Shark, and then there's a references section. Now the references section provides information such as information about different network protocols, the TCP and UDP port number reference, which I'll show you another place you can go for that in a moment. There's the read-write support for other capture file formats, information about capturing traffic on a switched network, and then information with regard to working with specific hubs. You'll also see on the wiki page that there's some areas that deal with third parties and reporting bugs, and there is a practical jokes section. I'll go back to the Wireshark page. There you'll see on the left-hand side we also have access to the bug tracker here. And then in the developer's information area, this is how we can get into the code. This is the link to look at the current development branch for Wireshark. The website is anonsvn.wireshark.org/wireshark/trunk/. If you're interested in reading the code, you can click on this link, and you'll see that it's designed in a directory structure format. Here we are in just the main area of the code. If you're interested in, let's say, looking at the dissectors for Wireshark, you would select EPAN, and there's the dissectors subdirectory. And let's say we want to look up the dissector information for bootp. There's the file, the dissector file, packet-bootp.c. Remember, bootp and DHCP are the same thing in Wireshark. DHCP is a subset of bootp. Here you can see where the information comes from, and a lot of the different areas in Wireshark, the code, a lot of it is very well documented. Here we can scroll through, we can see there's the code for Wireshark, just for that one protocol. I'm going to go back to the Wireshark web page now. And on the left-hand side, you also see a products section with products that complement Wireshark, such as AirPCAP, which is the wireless network adapter that we use with Wireshark when we're on a Windows system. There's also Network Toolkit. Network Toolkit is a collection of tools that runs on a Windows system that complement Wireshark. And then WinPCAP Pro. This is a version of WinPCAP that would be used by commercial product developers. So we've seen www.wireshark.org, and we also saw the wiki page for Wireshark. Now, Wireshark University has a web page online at www.wiresharku.com, and that's where you will find courses, training, etc. that deals with Wireshark and complementary products. IANA is the Internet Assigned Numbers Authority, and this is a website that you should be very familiar with. When someone goes to create an application and they want to use a specific port number, if they follow the standard rules, they would register that port number with IANA, and IANA maintains the master list of the port numbers. It's not just port numbers, though. IANA has a huge list of all the different protocols and value settings for various fields inside of TCP-IP and application communications. I'm on the IANA website right now, and probably the most common place that you'll go when you visit here is the Protocol Number Assignment Services section. I'll select this, and it will come up with an alphabetical listing, and I just need to indicate the first letter of the registry item that I'm interested in. So for example, if I'm interested in ICMP type and code numbers, I'll click on the letter I, and then I'll scroll down until I see the registry entry for ICMP. There we can see it's listed as code fields and ICMP type numbers. I'll click on one of these, and now I'm in the master document that was last updated on December 14th, 2006. Another strong reference is IETF, the Internet Engineering Task Force. This is where you'll find all of the RFCs, or requests for comments, for the TCP/IP protocol stack, and many of the applications that sit on top of that stack. This is the IETF website, www.ietf.org. And if we're interested in looking up an RFC, we could click on the RFC pages link and put in the RFC number. 1256 is the one I'm going to enter. This happens to do with ICMP router discovery messages. Another resource is online at www.packet-level.com, and that's the Protocol Analysis Institute, and that's where we maintain many trace files for network communications. In addition, you'll see Lawrence Berkeley National Labs keeps a list of trace files available online as well. When you access this website for Lawrence Berkeley Labs, you'll see that they have over 11 gig of trace files for you to play with. So there are a lot of great resources already out there to help you as you do your network troubleshooting and secure your network using Wireshark. In the next module, we're going to look at how to place Wireshark on a network when you've got hubs, switches, or routers involved in your network communications. Where you place the analyzer will affect what you're able to see. So in this section we will talk about where you can place the analyzer and how to deal with different network structures. Now the easiest way of capturing traffic would be to be on a hubbed network because everything goes everywhere on a hubbed network. But we don't find that many hubbed networks out today. Nowadays most of the networks will be switched. When we're in a switched environment, we're only able to see the traffic that comes down from our local switch port down to our analyzer. And there are 4 types of traffic that will come down that switch port: broadcast, multicast, any traffic to and from our own MAC address, and any traffic going to an unknown MAC address, which should be very rare on your network. Now because of this, if one of these clients is communicating with a server and we wanted to listen in on that traffic, we'd be blind to that information and blind to that traffic because the switch will be forwarding the traffic based on the MAC address. So because of that, we have to take some special steps in order to listen in on traffic when we're hanging off of a switched network. One thing we can do is we can hub out at the client. And that means that instead of going from the client directly up to the switch, we place a hub between the client and the switch. And we connect the analyzer up to that hub with the client. Remember that everything goes everywhere in a hubbed environment, so we should be able to listen in on all of the traffic that that client is sending or receiving. One thing to be aware of, though, when you begin hubbing out, is that there are a lot of hubs out there that are not actually hubs. They're actually switches. So you'll need to test it in a lab environment before you start taking that hub around and using it. One way to know if a hub is a hub is to simply set up a small hub network with 3 devices, your analyzer and 2 other devices, and then cause those 2 other devices to communicate back and forth between each other. Maybe you load an FTP server process on one and you connect to it from the other one using FTP. If you're able to listen in on all of the traffic between those other 2 devices, then your hub is acting as a hub. If you can't listen in on all of their traffic and all you're able to listen in on would be things such as maybe their ARP broadcasts, then your hub is actually acting like a switch. So be careful of that when you select a hub. Now we love the idea that we could hub out at a server, but it's doubtful that someone is going to let you disconnect the server from the network so that you can install a hub along the line. So instead, we have to think of other ways that we can listen in on the server's traffic. And one option would be to do switched port analysis, or to span a port on the switch. In this case, we plug the analyzer into the switch, but we need to reconfigure the switch to copy the server's traffic down the analyzer's port. Some manufacturers call this port mirroring. In a routed environment, we have a layer 3 device that is separating multiple networks. So if the network on the left-hand side of this slide is network 10.1 and the network on the right-hand side is network 10.2, by plugging into the switch and spanning all the ports to our analyzer system, we'll be able to see anyone talking to anyone on network 10.1 and anyone on network 10.1 that talks to anyone on network 10.2. But if there are intra-network communications on network 10.2, where a client on network 10.2 is talking to a server on network 10.2, that router will not forward that traffic down towards our switch that's spanned. So in that case, we have to move the analyzer so that we're on the right network to listen in on that traffic. We also have some challenges because of full duplex links. We can't go out and buy a full duplex hub. Instead, we get a full duplex tap. Now the full duplex tap will look at the transmit and receive channel information and forward it down to our analyzer. And there are 2 flavors of full duplex tap. A non-aggregated tap would take the traffic and split it into 2 different data streams, and we would have 2 analyzers set up to listen to the communications hanging off of that tap. Now, it's very important that if we are going to capture traffic this way, that we time sync those 2 analyzers, because when we want to reassemble the 2 data streams, the trace file 1 and trace file 2, into a single trace file, we want to make sure that the timestamp puts those packets in order. Consider using NTP or Network Time Protocol to sync those analyzers. Now, aggregated taps are nice because they take the data and they reassemble it, and when it comes down the line to the analyzer, the transmit and receive channels are already merged together. On the left-hand side of this graphic, there's an example of some taps for full duplex communications. These are available online at www.netoptics.com. In addition, being a protocol analyst, it's important not to transmit packets on the cabling system so you capture your own traffic as part of the information that you're researching or troubleshooting or trying to secure. Wireshark doesn't need an IP address in order to capture traffic. Or you could statically assign an IP address to your Wireshark system, statically assign a router or things like that. And also don't forget to turn off network name resolution so that Wireshark doesn't send out inverse DNS queries to try to resolve and get a name to correlate to all the IP addresses that it's discovering. In the next section, we're going to talk about the TCP-IP resolution process, and then we'll finish up this section by talking about where things can go wrong. In this module, we're going to talk about how the TCP/IP resolution process works when everything goes right. Now, typically, with normal communications on the cabling systems, you should see that the users are very happy with the performance. Users are often the first indication that something is going wrong. When we tap into the cabling system, we shouldn't see any retransmissions. You shouldn't ask for things more than once. And you shouldn't see big delays between the time you request some service and you receive an answer or an acknowledgement that your request was made. In addition, we shouldn't see any errors. We shouldn't see a request for service and an application respond by saying, no, I can't provide that service to you. We shouldn't see any service refusals where the server says, I won't provide that service to you because I don't understand what you're asking me. In addition, we shouldn't have a lot of background traffic, a lot of noise on that cabling system as far as broadcasts or multicasts. And we want to see that the communications take the most direct route. Using this scenario, we'll go through what would normally happen when a user communicates across the cabling system. Here we have a user on the left-hand side who makes the command FTP corp fs1 and hits enter. The user is sitting on network 10.1, the user is sitting on network 10, and the server is also on network 10. Just for simplicity's sake, I'm using the MAC address A for the user and the MAC address B for the server, just to make it a little bit easier as we go through this process. Now, the first two things that will happen are the port and name resolution processes. We can't send a packet out to the letters FTP. We have to send it out to a port number. So the etc directory on the local system contains a services file, and that services file is where we go to look up what the default port number should be for applications. Of course, applications can override those values, though. Now, once we learn what the port values should be, then we go through the process of name resolution. At this point, if the client has not indicated an IP address, we need to find out what the IP address is that matches the name that the client indicated. We have to go in a specific order. First, we have to look in cache to see if we know that information. If we don't have that information in cache, then we have to look for a local host file. Now, if we don't have a local host file, then we're allowed to transmit a DNS query across the cabling system. And that's why you see the yellow circle there with TX, because this is the first place where we might see transmissions occur across the cabling system. If we don't see a transmission occur across the cabling system, either the user put in an IP address directly, or we found the information we were looking for in cache, or we found the information we were looking for in a host file, or we didn't have any DNS server that we could ask, and the whole process just stopped right there. Once we go through the resolver process and we have the IP address of the target, we compare that IP address to our local mask to figure out whether the target is local or remote. And if it matches the local bits and it's on the same network, then the client needs to get the MAC address of that target device. Now, in order to do that, we have to follow some rules. The first thing we have to do is look in ARP cache to see if we already know the hardware address of the target. If we don't have that information in cache, then we're allowed to send out an ARP broadcast to discover the hardware address. Here we have another yellow circle because at this time we may see transmissions across the cabling system. If you don't see someone doing an ARP broadcast across the cabling system to learn of a target hardware address, then we believe that they have it in cache and they were able to transmit the packet with the correct MAC address because they already discovered that. If the target system is not local, then we have to go through an extra step, route resolution. In this case, we've got to look up how to get off of our network, and do we have a specific path to the target or a specific path to the target network, or do we just have a default gateway? So we look in order for a host address or a network address, and then if we don't have either of those, then we look and see, do we have a default gateway? And if we have a default gateway, we will send the packets to that default gateway. In order to send the packets to the default gateway, though, we have to have the MAC address of that gateway. So again, we finish up the process with MAC resolution. Look in cache to see if we have the hardware address of the default gateway in cache. If not, we're allowed to do an ARP broadcast to locate the default gateway. This is the entire TCP-IP resolution process. And if you follow along with this as you're looking at the trace files, you should be able to spot where problems have happened in the trace. The purpose of the whole process that we just went through was to get these circled values. Starting from the bottom of the packet moving up, the first thing we did was port resolution in order to figure out what that destination port number was. Now, the local system will assign a source port number in most cases, although not always. Some applications have predefined standard ports that we use for both the source port and the destination port fields. In other cases, we use a dynamic port for the source port. We also had to go and figure out what the IP address was of the target by using the resolver process. We had to resolve the name to an IP address. And then finally, the last thing we did was we went through the process to find out the destination MAC address of either the target on the local network or the router that would forward the packet off of this network. So if everything goes well, we should see the packets built and they're going to the proper destination. In the next step, we're going to focus on faults in the resolution process. Where can things go wrong? Now, in the last module, we focused on the way the TCP/IP resolution process should work. Now let's talk about where things can go wrong. We're going to use the same TCP/IP resolution process chart that we looked at in the last module. Now, the first thing that can go wrong is up in the port resolution process. So although the client typed in FTP and a target system, we know we have to go and look at the etc services file. If someone has played with that file or someone has altered the values in that file, we may find that we resolved to the wrong destination port number. In addition, we may resolve to the proper port number only to find that the server is using a non-standard port number. Or we may find that the application has overridden the value in the etc services file and we end up going to the wrong port number as well. There are many things that can go wrong during the name resolution process. The cache information that our client has may be actually outdated and incorrect, or perhaps at the time that the client originally got the information was incorrect and it's cached invalid information. We may have a local host file that a user has gone in to edit and they've put in a static IP address associating with a specific name. Now we find that their local system always goes to the wrong IP address because of that host file value. In addition, they could do a DNS query across the network system and either the DNS server is not there, or we could find that someone is spoofing DNS responses, giving our clients incorrect information. When we go through the process of defining whether the target is local or remote, if our network mask is set up incorrectly, we may think that a target is local when actually it's remote, or we may think that it's remote when Actually, it's local. If our network mask is too short, we'll believe that everything is local and we will ARP, 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 ARP for all of those devices that we feel are local. Now, hopefully, our router can help us out by doing something called proxy ARP in that case. If our subnet mask is too long, then we feel that the majority of devices are remote to us, and we constantly send our packets to our default gateway or to a local gateway to try to get off of the network. And that gateway will forward those packets directly back onto our network and send us ICMP messages indicating that it's not the best way to go. In addition, if we get down to the process of doing the MAC address resolution, we might look in cache only to find out that the value in cache has actually been poisoned. Doing ARP poisoning is not a very difficult process. If we do send an ARP request on the cabling system to the broadcast address, someone besides the target system may answer back to poison our ARP cache values as well. If we find that the target is remote, we might look up in our local routing tables to find out if we know how to get to that host, the network, or if we have to go through a default gateway. We may have an invalid value in the host tables or the network tables that have been caused by someone doing an ICMP redirection attack on us. In addition, we may have a default gateway value and the gateway is either not up and running at the current time, or it could be that the gateway is not the best way to go. We would still send the packets to that gateway, but it would have to send us redirections. If we get all the way down to the bottom right-hand corner here where we know that we have to go through a router to get off of the network, we look in cache first to see if we know the router's hardware address. Again, that information may be poisoned in cache. If we do an ARP query across the cabling system, we may get a bogus response coming back. So there are a number of reasons why things may go wrong on the network. And it's extremely important to understand what normal communications look like before you're thrown into a network where all of the communications are abnormal. As you go throughout the rest of the sections in this course, I will start each section by examining the packet structure for that protocol or application. Then we'll talk about how to filter out that type of traffic so that you can see just that traffic instead of all the other traffic in the background. Then we'll go through a process of looking at normal communications for that protocol or application. And we'll finish up each section by looking at unusual traffic for that protocol or application. And I'll explain why it is unusual and where the communications have gone awry.